Basic Robot Course, Module 6, Operating Modes, Robot Control. What are we going to see in this module? We will see the differences between the automatic and manual mode, and then within the automatic mode, we will see that there are different ways of managing the robot automatically, and therefore we will talk about the operation panel mode of the IO mode and the PC mode. What are the differences between manual and automatic? First of all, in the previous modules, we have seen that to switch between these two models, we need to wire a two position selector by the customer, which is used to switch between the two modes. This selector was previously installed on the controller from the CR800. It is no longer present. After having wired the operating mode selector, it will be possible to switch between manual and automatic. The manual mode is used to work inside the machine with the teaching box or teaching pendant for maintenance operation, taking points or debugging programs. If we turn the selector automatically, we will work in the normal conditions of use of the robot, so with the cell in production. Let's see what differences there are between these two modes. First of all, in this diagram, I have summarized all the important elements that come into play between the two modes. Let's look at the manual first. We say that manual means working with the teaching box to work with the teaching box. We should place the selector on off, then the double channel linked to the operating mode will be opened. The signal will be the two channel 1, channel 2 will both off. We should enable teaching box. So what does that mean? On both teaching box version, both on the R56TB and the R32 TB, we will have an enable button. This enable button located on the front in the case of the R56 located on the back. In the case of the R32 or R56, to enable the teaching box, this button must be pressed. Once it has been activated, it causes this button to light up to work with the teaching box, and therefore to move the robot to turn on the motors, it will be necessary to press the dead man halfway. But sorry. But what is the dead man? In this lever that we find in the rear part of the teaching box, which is characterized by having three positions. In the released position, therefore with the dead man button off, it will not be possible to turn on the motors. Within the intermediate position, it will be possible to turn on the motors. In the third position, which is fully pressed and pulled, the motors will be turned off again. So we will have to press the deadman button halfway. So in position 2 of this diagram, it will not be important to have the doors open or closed, because the safety devices implemented on the teaching allow the operator to work in total safety, even when open doors, and we will see why. The emergency mushrooms obviously must not be pressed. They must be okay. The speed of the robot, when we work with the selector in manual mode, is downgraded to 250 millimeters per second. Please note that the teaching box display always shows a speed value called override in percentage. This 100%, which in manual correspond to a maximum of 250 millimeters per second in automatic, will then be transformed into the actual speed of the robot, therefore 8, 9 or 10 meters per second. The IOENA signal in manual mode obviously doesn't come into play. So what should we do? Select to work with the teaching box, the selector on manual. We should enable the teaching box, press the deadman halfway, and it will then be possible to turn on the motors and move the robot in jog mode or in debug mode to test debug our program. Working automatically, these things change. Then we will go to see what the various automatic modes are. First of all, the selector must be positioned on automatic. The button must be off. This enable button is a kind of safety for the operator. What does it mean? That if we are huddled behind the robot, it's one of our colleagues. He doesn't see us. He doesn't see us and wants to put the machine on automatic by turning the selector. An alarm will be generated automatically as long as the enable button is pressed on the teaching box. Therefore, the safety of the operator which inside the cell is guaranteed precisely through this enabling button. The enabling button must be turned off in order to go automatically. The deadman no longer comes into play. Why? Because the door will be closed with the mushroom OK. The speed of the robot at that point will be the maximum speed of that specific one. Automatic means 3 modes: operation panel mode, IO mode, and PC mode. Be careful that by managing the robot automatically, it comes into play a signal that is important called IOENA, Operation Enable. Is an input signal, therefore to be wired in input to robot, where it can be wired on IO digital input, can be wired to a field bus signal. This input determines whether the robot is controlled externally or not. That is, by activating that signal, will be removed the ability for other interfaces to take control of the robot. In OP mode, the signal must be kept low. In IO mode, must be turned on. In PC mode, must be kept off. Let's see what these three automatic modes are. What the OP modes are. Let's start with what is called the operation panel integrated in RT Toolbox 3. So if we put the selector on automatic and close the doors, and we have no error because we have all the mushrooms released, we can turn on the motors from this interface and move the robot from this control panel. The operation is completely safe because the doors are closed. We also find the same panel inside the teaching box R56TB. A very similar interface that allows us to turn on the motor, select the program and select the programs and run them. Third mode is a third mode always defined as OP. It can be managed through ActiveX, which we find on the installation CD of the RT Toolbox 3 networks in the Melfa RXM utility folder. You can then take control of the robot or using this mode and managing the robot through an external PC within which we have developed our robot management interface with one of these environments. So we could use Visual Basic, Visual C++, Visual StudioNet, the C++ from Borland. By the way, installing this XM Alpha will also install a folder of example, and there will be several examples written in the various languages available from OP mode. Let's go to IO mode. What this means is that by inserting an optional card with the 32 inputs and 32 outputs inside the controller, it will be possible to take control of the robot from outside by parameterizing this table that we find under parameter signal, parameter dedicated to IO signal assignment. So it will obviously be possible to configure this option enable, which we said before had to be a signal arriving from the outside, and we could configure a series of inputs and outputs to take control of the robot from the outside. So if we imagine wiring through digital I/O with a PLC, the PLC will have to activate this operation enable. At that point, it will be able to give us a series of signals, such as starting the motor, also receiving a series of feedback. We decide which ones to configure, we decide which ones to use. Within this menu, there are different gestures, different signals that we can use. Also in IO mode, we also find the possibility of installing a field bus in the controller. The field buses are available in the controller are those that we can see in this slide. And the cards that are optional are all of the slave type. Be careful that we are talking about a field bus to be installed in a standalone controller. So in a D version, we could install a CC-Link, a CC-Link field, a Profibus, or a Profinet, a DeviceNet, an Ethernet P, an EtherCAT. The CC-Link I feel basic, which is the only one integrated on the Ethernet port, because being 100 megabit per second, but bus, it is possible to integrate it through a simple firmware implementation. It is the only bus available completely free in all the products of Mitsubishi. Everything that we don't find in this slide, we will, however, find in the PLC platform. Therefore, in the air version controller, so if we need to manage a master card, for example, we could install a PLC card. Usually PLC cards are both master and slave, and therefore decide to manage the cell and the robot as master of a network of remote I/O devices or signal on a bus. Obviously, a whole series of basic ones that are typical of the PLC world are available on the PLC version, such as CAN and Modbus TCP, Modbus RTU, and so on. So what we don't find in this slide is available on the PLC platform. Always here in IO mode, I also have this Ethernet communication with a Mitsubishi family HMI. We have a protocol called the God Direct Connection, which allows us to take control of the robot from this operator interface. The interesting thing is that there is documentation and templates already prepared by Japan to be able to manage both a robot, therefore both a standalone controller and an R series controller. Related to the automatic, it is called PC mode, precisely because it involves the interaction of the controller with an external PC to create communication with the robot from the outside. For example, with a vision system. With a PC supervisor, we have three different approaches. We can open a communication socket, and therefore we talk about the HASH data link protocol. We can use what we call an asynchronous protocol or R3 protocol. We can use a synchronous protocol, also called TMX, which it can in turn be used with two different approaches, therefore in pure reading, and we will therefore talk about real-time monitor. In reading and writing, we will talk about real-time control. Let's see what the communication socket is. This communication method is typically used to interface the robot with the general purpose vision system. We need to write a program in the robot, opens a communication channel over which we receive a string from the vision system, formatted exactly as the robot expects it. If we don't respect this syntax, the thing doesn't work. We must know how to format the field and the fields, and we must always have identical syntax in the program external to the robot and in the robot program. The solution is fine as long as we have limited needs for content and for content that we want to exchange. Does it work if we have to, for example, exchange coordinates, measurements, etc.? And the most used communication method is because it is the simplest. Generally, the robot is seen as the master of the cell, so who requests the coordinates from the vision is the robot. The types of communication is typically used if a simple protocol is to be implemented and data is to be exchanged, which always arrives formatted in the same way. Typically, this happens with a vision system. So I will receive a series of information such as good piece, good piece or not good, the XY zeta coordinates from the piece rather than the color of the piece. So if I have a series of data that are constant, then my string is always formatted the same way, and I go to define the string robot side and vision side. This protocol is extremely simple because it is basically made up of four instructions: two instructions to open and close the communication, and two instructions to read or write data to external PC towards a vision system. Let's see what the second protocol is called the asynchronous protocol or R3 protocol. This protocol allows us to interpret the native language of the Mitsubishi robot. Mitsubishi makes open the entire communication protocol of the robot, which is the same protocol used by RT Toolbox 3 software or by the teaching box. This protocol does not require any programmer resident on the controller. This communication channel is always available and has infinite potential. We can give any type of command to the robot. We can create programs, load them into a slot, put them into execution, stop them, turn on the motors, and so on. Everything that the machinery regulation for safety issues security allow us to do with the robot, we can do it. Using this communication protocol, the limitation is that asynchronous, so the timing with which we are going to exchange information is the timing of any TCP/IP communication channel. Therefore, our packet will be subject to network traffic. However, the performances are high. What we cannot do with this type of protocol is move the robot with the commands from the outside. We can create a movement program and have it run. We can create a motion program with a single point to then move the robot from A to B. But if we want to create a robotic part from the outside, this protocol does not. Everything related to the management of the arm, it is done by the controller of the robot in such a high performance way that thinking of replicating it ourselves from the outside. Even in a similar way, is truly very ambitious. If we want to make all the inverse cinematics in such a way that is work in all circumstances exactly like the robot control work is ambitious. Normally in application, the robot controller is always used to do anything involving motion. For example, we could create many very simple programs that are each capable of carrying out a mission, programs that we could then manage with an intelligence on board the robot, but with a supervisor who is typically external to the robot. The cell manager may no longer be the robot, but something else. Often, if we think of a classic pick and place, the master of the cell is the robot. So the robot is in charge. If, however, the robot has to deal with a number of sensors external to the robot that cause the difficulty of the cell, not in the motion part, but in something else, we opt to leave only the motion part to the robot. The synchronous protocol can be enabled in two modes: non-procedural, the raw command is sent to the controller, or procedural, which use a specific syntax that that makes us more confident that the communication packets has been exchanged in a robust manner. Procedural means being able to give a unique identifier to the packet we send. It means declaring how long the packet will be. It means declaring the robot we are interfacing with. It means giving the command. It means postponing checksums with which the interlocutor is really. I'm sure everything went well. Here we see in this slide free software that is the Hercules setup, with which we could go and do simulation tests. The interesting thing is that to do these tests, we don't need to have a real robot, but we could use the simulator integrated in RT Toolbox 3, because the Hercules can easily talk to the local host and then send commands to the robot simulator. The commands are given according to a precise syntax that you see here in red. So we'll need to give the ID of the robot we are interfacing with. It will be necessary to specify the slot precisely, because we could work on multiple slots. We will have to specify the command. Therefore, the action we are asking the robot. For example, we ask the robot to make a speed change, and what the parameter of this action are, for example, the new speed value. Here you see a practical example of this application, where we see an interface created in LabVIEW using this asynchronous protocol. So let's see the last protocol, the most complicated one, which is the synchronous protocol called MXT. So it is the third possibility. We have to manage the robot from the outside through Ethernet communication. This protocol represents the most total opening of the controller, but it also certainly represents the most difficult way to interact with the robot controller. The protocol is MXT, is a communication channel such that the robot controller turns off all the intelligence, leaves only the drives active, and listen to the set point of each single positioning from the outside. So from external, we generate the robot set point instant by instant at a known and fixed rate, and the robot controller will movement by instant reach the individual set points that we want to impart. Normally, we are using to telling the robot that we want to go from A to B. from A to B, that we want to go there on a segment, that we want to go there in the most performing mode possible, that we want to go there along an arc, that we want to make a spline, that we want to take a certain path, and then the robot controller that is managed, for example, all the acceleration on the individual axis to achieve the goal. In the MXT protocol, the controller listen for where we want the arm to be positioned from here at 3.5 milliseconds. We must therefore generate an array of set points that have a time frequency of 3.5 milliseconds. We are going to generate infinite points, these infinite points, and the robot every 3.5 milliseconds will reach the commanding position. That's right, 3.5 milliseconds is the communication layer clock. This is not the processor clock. This protocol is useful in all those applications where we need to feedback the motion with an external sensor. In general, whenever we do not have a linear phenomenon, that is, whenever we are not we are unable to predetermine the path, and we have to modify the trajectory dynamically with respect, for example, to an external sensor. Every time we perform an action, but we want the effect of our action to be controlled when we cannot have a mathematical model of our object, which lets us know the consequence of our action. We could, for example, get closer to the target and then follow the last part of the journey guided by a camera. This protocol is open from the point of view of reference system. We are not obligated to give the set point, for example, expressed in joints. An example is already provided in the manual. If we use this protocol in read-only mode, the controller will manage the motion, but we will be able to know every 3.5 milliseconds where is the robot located. Up to 8 devices can be connected to the controller at the same time. Ports 10,001 to 10,008 are used. The asynchronous protocol, so the R3 protocol, is in TCP, is a deterministic protocol. Instead, the synchronous protocol MXT is in UDP. The protocol seen, therefore, the fact of being able to open a communication socket, then AC data link protocol, the R3 protocol. The protocol is MXT. These three protocols can coexist together, but if we are in synchronous in pure reading, we cannot work in synchronous in reading and writing. So if we are in real-time monitor, we cannot also work in real-time control to make the robot follow the point of the coordinates. There are two different approaches, or the set points come from outside directly from the Ethernet port, or the set points are contained in a file that was generated with the add-on for SolidWorks called MelfaWorks or RT Toolbox 3 Professional. This file obviously must then be downloaded into the controller. Basic Robot Course Module number 7, Manual and Use of the Teaching Box. What are we going to see in this module? We will see the differences between scar and anthropomorphy. We are going to see how to move the robot in jog mode. We are going to see the three main jog movement, the three main jog movement modes, which are joint, the Cartesian, and tool. We will then see how to use the teaching box to move the robot, and how to use an extremely useful functionality, which is that of aligning the robot's wrist using the teaching box. Let's start by analyzing what are the differences between scaras and anthropomorphs. What is a roboscara? Is a system characterized by the presence of four interpolated axes with the sequential mechanical assembly and therefore with the 4 degrees of freedom. They can carry out all the movements on a plane in which they remain tangent with a tool at each point of circumference. It can be analyzed from this image. So we will work within this geometry by picking up and depositing a piece without having the possibility, however, of being able to rotate it. Let's analyze the acronyms. We have already seen in the previous modules that RH stands for horizontal robot. Why don't the Japanese call robots Kara, as we call them, but they call them horizontal robot. FR stands for the series. The presence of the H identifies the presence of four axes, and the R, if present, identifies sailing mounting. As already mentioned in the previous modules, the Roboscara in the Roboscara, all the axes are without brake, with the exception of axis 3. For releasing the brake, there is this little button that you see in the figure. As regards anthropomorphic robots, they are systems characterized by the presence of six interpolated axes, sequential mechanical assembly, and therefore with 6 degrees of freedom. They can perform all movements on a plane, including remaining tangent with a tool to a sphere. You can see it in this image. So let's move on from moving tool parallel to a circumference to a tool that can instead remain parallel indeed, or rather it is more correct the term tangent to a sphere. Here too we analyze the acronym and magazine for a vertical robot. FR for the series, we could have the absence of a letter that identifies the standard arm, or the L for the long arm, the double L for the super long arm. All anthropomorphic robots have all the braked axes except for the 2 kilogram, which exists in two versions. The absence of the letter B in the acronym identifies that axis 1, 4, and 6 does not have the brake. The presence of the letter identifies that all axes are braked. In this image, you see how a J4 series motor is made, which are the motors used by Mitsubishi. Where we start from the motor element, in the next central part, there is the electromagnetic brake part, which is simply a parking brake that is engaged when the torque of the axis is removed, and in the final part we see the encoder part. How we can move the robot in jog? We can use 6 different modes that you see in this drop-down menu. They are the same 6 modes that you will then find on the teaching box. The three most used are the joints mode, the Cartesian mode, and the tool mode. In the joints mode, it is possible to move each axis independently. In the Cartesian mode, it is possible to move the robot's grip point, which we will call tool center point, compared to the Cartesian triad positioned at the center of the robot base. In the tool mode, we will be possible to move the robot's grip points with respect to the triad positioned natively in the TCP. We will see that the TCP will be in the center of the robot's fringe, but we could position it as in this figure, for example, at the end of our jaws, which will be the picking point of our piece. In this image, you see the Cartesian triad positioned inside the base of the robot, which is in line with the rotation point of axis one, and this is the triad that we will take as a reference in the Cartesian mode. And here you see another triad, which is the one that used for tool movement. I finished here. For more information on the movements that the robot can make, on what is possible to do with our RT Toolbox 3 programming software, and also to practice and become more familiar with our software, I send you to this link where you will be able to access video tutorials for programming our robots. I greet you here. I hope the course was interesting, and we will contact you perhaps in case of technical support. Have a good day.